Hi everybody, it's Dr. Pusey and here's my run through of the WACE Physics 2021 exam. So question 1 for this exam involves the energy level diagram for hydrogen, and you have an electron incident on this hydrogen atom. One thing the question does not make very clear, unfortunately, is that the hydrogen atoms are in their ground state. So you're looking at transitions from n equals 1. Now in this question, what you've got is electrons incident at the ground level, and then what's going to happen is the energy from those electrons will either be transferred through absorption into the hydrogen atom, or there will be an elastic collision and the electron will just bounce off with the exact same amount of energy as it did when it was incident on there. So what you want to do is you want to find out how much energy is required for a jump from, say, n equals 1 to n equals 2. And what you find out is that's equal to 10.2 electron volts. So that's 13.6 take 3.4. And so if you need 10.2 electron volts, if you've got 12.2 electron volts in the electron, then yes, that transition is going to be possible. And then if you find out what the energy level difference for the next one is, from n equals 1 to n equals 3, so from the ground state up to, you'll end up finding out that you need 12.09 electron volts for that to occur. And since you've got 12.2, yes, that can occur as well. Now what you'll find is that if you try to get the hydrogen atom down from n equals 1 to n equals 4, that's going to be equal to 12.75 electron volts, which is not possible because it's greater than 12.2 electron volts. So there's two energy level transitions that can occur, plus the elastic collision. So what you want to do when you're writing your answer down, well, when you're doing your calculations, is you find out how much energy is left over. So 12.2 electron volts in the electron, subtract the 10.2, and you'll end up with 2.0 electron volts for the first one. And the next one will be 12.2, subtract 12.09, and you'll end up with 0.11 electron volts. And finally, the elastic case is where you have 12.2 electron volts, but no energy transfer has taken place. So it's going to be 12.2 electron volts. And so when you're writing your answers down, as long as you make it clear, 2.00 EV, 0.11 EV, and 12.2 EV. And there we go. Question 2 is a question that is just asking for a simple conversion for mass, units of mass. So in your data booklet, the mass of a bottom quark is given to you as 4.18 giga electron volts per c squared. So to convert that to kilograms, what you want to do is you get that 4.18. It's in giga, so you need to multiply that by 10 to the power of 9, and then that's in electron volts. So to get that in joules, which is what you want for your SI units, you multiply it by 1.6 times 10 to the negative 19, and you divide that by c squared, so 3 times 10 to the 8 squared, and what you should get is 7.43 times 10 to the power of negative 27. So a pretty easy 3 marks if you ask me. There we go. So question 3 is a motor question. They've simplified it a fair bit by telling you that it's just going to be a single rectangular loop. They have tried to complicate things by saying that the loop is at an angle of 45 degrees to the magnetic field, but that plays no role in this question. They have made things nice and easy by saying that by telling you the current's going from positive to negative, just in case you get that mixed up, which means the current going through the coil will look a bit like this. Now, the question's asking to calculate the magnitude and direction of the forces on each side of the coil. So the calculation is very basic. It's just F equals ILB. And like I said, even though it's at a 45 degree angle, the current is still going to be perpendicular to the magnetic field. So the current going through it is 3.5 amps. The length is 0.05 in meters. And the magnetic field is 1.52 times 10 to the negative 3 Tesla. And if you put that in, you'll get 2.66 times 10 to the negative 4 newtons. So that force is going to be on one side of the coil, and down here on the table it's only asking, well, it's going to be on both sides, isn't it? So 2.66 times 10 to the negative 4, and then you're going to see another 2.66 for the other side of the coil, because in both cases the current is running perpendicular to a magnetic field. Now the direction, if I come back up, I can see I'm going to do AB first. The current's going, I suppose, into the page using my thumb if the current's going into the page, and my fingers are pointing to the right. Then my palm, which is the direction of the force, is going to be pushing down. So over here, I'm going to write down. And that would mean on the other side of the coil, it would be pushing up. And those are the answers. Alright, question 4 is a bit of a mathsy one. You've got a proton in a particle accelerator that's being given an energy of 0.1 tera electron volts. You can interpret that as either being the kinetic energy or the total energy of the particle. The answer you get to 5 significant figures is going to be the same. So I'm going to do it using the total energy, which makes it a little bit easier. So the first thing I'm going to do is convert that energy value to joules. So 0.1 times 10 to the 12 tera. And 1 electron volt 18, and you should get 1.6 times 10 to the negative 8 joules. Right, so now that I'm there, I'm going to get the formula for the total energy, relativistic energy of the particle, and that's going to be equal, I'm going to put in some numbers now. It's 1.67 times 10 to the negative 27, 3 times 10 to the 8, square it, don't want to forget that, over the square root of 1 take v squared on c squared. And that's going to be equal to your 1.6 times 10 to the negative 8. So what I'm going to do now is I'm going to get the top part of this fraction and divide it by the 1.6 times 10 to the negative 8. So I end up with 9.39375 times 10 to the negative 3. I want to try and keep as many decimal places as possible. Now that's going to be equal to square root of 1 over v, 1 take v squared on c squared. So first thing I'm going to do here is square both sides, and I end up with 8.824254 times 10 to the negative 5 equal to 1 take v squared on c squared. I'm going to get this v squared on c squared and bring it to the other side so that it's now going to be positive. And that means I'm going to have 1 take this number here, and you end up getting 0.999912. And v by itself ends up being, if I square root of both sides, is 0.9999559 C. So your answer that you'd put down to 5 significant figures is 0.99996 C. Now, the next question, in question 5, it's asking to state 2 main differences between hadrons and leptons. So hadrons are made up of quarks, whereas leptons are fundamental particles. And if you want to extend from that, since hadrons are made up of quarks, you can say that hadrons experience the strong force. And you have to clarify that leptons do not. So it's really important that when you're answering these questions where it's asking to talk about differences, you talk about both particles. It's very easy to misinterpret this question and say, you know, hadrons are made up of quarks for number 1, and then number 2 say that leptons are fundamental particles. You'd only get 1 mark for that. Okay, in part B, your hadrons, well, you've got a proton, so you've got 2 ups and a down. Your meson will be like a quark and an anti-quark, so that's definitely going to be there too. Tor neutrino is listed as a lepton on your data booklet, so that should have been easy to get. A neutron will be up here, quarks. A muon is also on your data booklet under the leptons section. And the baryon will be up here because that's what a proton is. Okay, so you only need 1 of those, but a couple of easy marks there, especially for the leptons, since that's given to you in the data booklet. There we go. So question 6 is a pretty nice question. You've got a beam or a plank that's sort of on this slope here, and then you're going to have a block of something that's just going to fall down until it reaches the point C. When it does reach the point C, the force due to that block, or the torque generated from this force, is going to be equal or start to become greater than the force here, which is the center of mass of the beam. So what it wants you to figure out is the distance between A and C here. So what I'm going to do is I'm going to select B as my pivot point, and I'm just going to solve it with knowing that this angle here is going to be the same as this angle here. So let's get to it. So if we come down, the first thing you want to do whenever you have these sorts of questions is make sure you just write down that you know that you're going to be solving it using equilibrium, because that's usually a mark right there. Although I think that the amount of space they give you for this question is a little bit low. So the anti-clockwise torque is going to come from the center of mass of the plank. So that's going to be the radius of the plank. Oh, sorry, the beam. The radius of the beam, the mass of the beam, and G sine theta. And that's going to be equal to the distance from the pivot for the block. What should I call this one? I'll call this the mass. And the mass of the mass, and G sine theta. So suddenly the G sine thetas do cancel out, which makes things easier. The radius that the beam, so the center of mass for the beam is 1 meter, 5 meters long. So we'll say 1 meter there. And then we got the mass of the beam, I think is 15 kilograms. We'll check that, yep. And that's going to be equal to the radius, which is what we want to find out first, multiplied by 5 kilos for the block. And what you'll find is that RM, or the radius distance from the pivot, is going to be 15 on 5, so 3 meters. But that's not the answer. AC is going to be equal to AB plus BC. So that's going to be 6 plus 3. So your answer should be 9.00 meters. The next part of the question, which I think probably should be worth a little bit more than 2 marks, but it's asking to calculate the angle of the slope as measured from the horizontal. So I'm going to zoom out a little bit here. So what we're looking at is it's now an inclined plane problem. You've got an angle of slope. So if that's the case, and it's asking you to, and what it does give you at the start here is just 3.3 seconds. It tells you that while it's accelerating, it takes 3.3 seconds to travel that distance, so that 9 meters. So really what I'm going to do first is just sort of, so you're going to have the acceleration due to gravity coming down, and then you're going to have the normal force pushing up, providing a normal that's perpendicular, and then the result of those is going to be this acceleration, which is what we're observing. And that's going to be G sine theta, where theta is this, which is the same as your theta over here at the top. So with that in mind, I'm now going to first work out the acceleration for the 9 meters. So if I start with S equals S equals half AT squared, since it doesn't have a starting velocity, then I get the acceleration is going to be equal to 2S on T squared. So it's going to be 18 on 3.3 squared, which is going to be equal to 1.65 meters per second squared. All right, so that acceleration is going to be equal to this G sine theta. So G being 9.8 sine theta is equal to 1.65. So sine theta is going to be equal to, you get 0.169. And that would mean theta itself ends up becoming 9.71 degrees. And that almost seems a little bit consistent with the diagram, which is all good. All right, there we go. Okay, so for question 7, it's not the best question in the world, but essentially it's some would say this is more about stability than it is about static equilibrium. But at the end of the day, what you want to do is you want to first draw, to illustrate your answer, you want to draw a low center of mass. So the center of mass of the Bobo doll should be below that midpoint, so that when it is tilted over, the center of mass is going to be acting in such a way that it will create sort of a restoring moment or restoring torque whenever it gets rotated up. So you get 2 marks for that diagram. I'd imagine that if you drew the force that's applied by the person holding it down, you wouldn't lose any marks for that. But the key, according to the marking key, as long as you've got the weight force showing there and it's showing that it's a restoring torque that's being applied. So in my answer, I've said that when the doll is held down, the torque produced by the low center of mass is matched by the force applied to the head. Or you can say it's in static equilibrium at that point, something along those lines, because the question does say that you need to talk about the conditions required for static equilibrium. So I've said that those two are matched. And then when the head is released, the system's no longer going to be in equilibrium, and the torque due to the center of mass will rotate the doll upright. And if you've ever seen those dolls, it'll correct itself and then probably overcorrect and then sort of wobble a bit before it stabilizes to the point at which you get the doll on the left hand side where the center of mass acts straight through the base. Okay, and for question 8, complete the table for an antiproton. Okay, I think this is probably perhaps the easiest 4 marks in the question in the exam. So your antiproton looks like that. Your quarks are the same, but they're all the antiparticles. The charge is going to be the opposite. You can't have an opposite mass, so the mass is going to be the same, 0.938 gigaelectron volts per c squared. And there we go. Okay, question 9. I actually like question 9 because it's pretty much identical to a question that I've been giving my students for the past few years as part of my regular delivery. If you have a person that's sort of sitting on a platform, they're going to be experiencing an acceleration upwards, which is the equivalent to the acceleration due to gravity in the opposite direction, and that's because it's Newton's third law. Gravity is acting on that person; they're acting on the whatever they're standing on, and that means that gravity is going to be pushing back. Now, in this case, what we're trying to do is we're trying to simulate that in the absence of actually having any gravity. So what we need to do is we need to put this person inside a circle of a certain radius. In this case, it's 460 meters, and we need to have them zipping around and having a velocity. So that means that the centripetal force is going to be equal to that 9.8 meters per second squared. So for that to occur, we need to be going a certain velocity, v squared on r. So if we substitute instead of v, we have 2 pi r on t. So we're going to have, 4 pi squared r squared on TR, and then that'll simplify down to 4 pi squared R on T squared. So we want that equal to be 9.8. So if we rearrange that equation, we end up with T is equal to the square root of 4 pi squared multiplied by 460 divided by 9.8. And that's the square root of 1853, which ends up being 43.0 seconds. There we go. Okay, so question 10 is a magnet falling through a copper pipe. To help illustrate what's going on here, none of this is really asked, but let's just say you have your north pole there and your south pole there, and that's going to create eddy currents above and below the magnet. So in this particular case, you're going to have the current going in this direction so that it generates a south pole at the top, and underneath it's actually going to do the same thing. You're going to want a current produced like this so that it creates a north pole above it, or sorry, a north pole below the magnet to repel it, and a south pole above it to sort of attract it, and that's going to slow the magnet's speed as it falls down. I think it says it reaches a terminal velocity. And that's helpful for us. That means that it's losing a constant amount of potential energy every second. There's a couple of ways that you do this. The way that I did it is because it's asking for the power, I've decided to go for, well, how many joules per second is it going to be losing? So to do that, I just find out what is the EP, or the potential energy lost per second, since I know that it is falling to the ground. And that's going to be equal to the mg and the delta H per second, right? And that part there is going to be the 8.51 centimeters per second, because that's how fast it's falling. So with that in mind, I sub those values in. 0.055, 9.8, and 0.0851, and what I end up getting is 0.0459. Going to be fancy and write it in scientific notation, times 10 to the negative 2 watts, or joules per second, which is great. So part B is telling us that silver has a higher electrical conductivity than copper. So if we refer back to this diagram, remember eddy currents are being induced here, which create the magnetic fields that are going to start opposing the motion, or they slow the magnet down. So if you reduce the conductivity, so if you increase the conductivity of the material that the eddy currents are forming in, then what you're going to be doing is you're going to be increasing the current. So the current will increase, or the eddy current will increase, right? So if you have more current going through that tube, then that means that your magnetic field that you're creating, that you're inducing, will also increase. And if you're inducing more magnetic field, then you're going to end up with a force that's created that also increases. So if the force on the magnet increases, then you can expect the speed will decrease, and if the speed is decreasing, then you can expect that the power will also decrease as per the above calculation. Okay, and question 11, we now have some higher speed charged particles. It's basically asking, through what potential difference will a proton at rest need to be accelerated? So you have a proton that's been accelerated through an entire potential, which means all the work done on that charge as it passes through the potential will end up being converted to kinetic energy. In other words, the change in kinetic energy that this particle will have is going to be equal to the work done on the charge, which is going to be equal to QV. And if you want to be fancy, you can write all these equations, and then you just want to get V by itself, or the big V by itself, to find out what potential that is. So it ends up being mv squared on 2q, and then you sum in the values, and the charge of a proton, same as the electron, and what you'll end up with is 1879 volts, or to three significant figures, 1880 volts. And the good thing is the next part of the question actually sort of tells you you're aiming for around 2 kilovolts, so you're on the right track at this point. But in this time, the question's asking you, okay, what if you used an electron instead? What sort of velocity will you get out of putting a much smaller particle in that electric field? Remember, the same charge, right? So if we start with this one again, QV equals half mv squared. So now we're going to rearrange it so we have velocity by itself. It becomes a little bit more tiresome, so square root of 2qv on m, and again you're summing your values to 1.6 times 10 to the negative 19, and then I'm putting 1879 in. Doesn't really matter what you put in, as long as it's either the value above or the 2000.11 times 10 to the negative 31, and I got 2.569 times 10 to the 7, so my answer to 3 sig figs is 2.57 times 10 to the 7 meters per second. So it's not above the speed of light, which is good. And it's above the speed of the proton, which is good. So that tells me it's not terrible, put it that way. Question C, what is the ratio of the kinetic energies between the proton and the electron? Okay, so here's the thing. So the work done, so the kinetic energy is going to be equal to the work done. So the work done is going to be equal to QV. So they're the same charge, and they're going through the same potential, which means the energies are going to be the same. So the ratio would be that. And there we go. Okay, so question 12, which is the last question of section 1, is about cosmic microwave background radiation. Now, the examination report says this was very poorly done, with an average of 1 out of 4, and I think that's just for the people that attempted it. And it's no real surprise. As far as I'm concerned, there isn't a very strong link between what the question is asking and what the marking key has for the answer. And I think it's just because it's a little bit too vague. But look, let's just go through it. The first question is asking to explain the origin of the cosmic microwave background radiation as part of the Big Bang Theory. So you do need to talk about how the Big Bang Theory actually predicts the cosmic microwave background radiation. So the angle that they've approached is to say, well, look, the Big Bang Theory states the universe was very hot and dense in its early stages. So just as inflation started to occur and light could permeate through the universe, the light will be high energy, which means it'll have a low wavelength. So you need to illustrate, or need to specify that radiation or black body radiation would have been given off in all directions. And for part B, it's asking, how does the study provide evidence that the universe is expanding? So how does finding this cosmic microwave background radiation actually give us evidence of expansion? So not the Big Bang as such, but the expansion. So we need to be very careful here and talk about, okay, well, we mentioned in the above bit, but that we're giving off this very high energy, low wavelength radiation. And if the universe was expanding, then those light waves would actually expand out. So what we would see is lower frequency radiation, which is what we observe. So my answer is to say the Big Bang Theory suggests the wavelengths originally emitted were much shorter based on the temperature, and expansion of the universe since then would result in the lengthening of these waves, resulting in the longer wavelengths we observe today. Now, like I said, these answers, I've written these answers knowing what the answer key says. I would expect, based on what the examiner's report says, that not many students will get this out. So if you're one of those students who didn't really get the right thing out of this, I wouldn't feel particularly bothered by it. I'll just move on to the next question. So section 2 in this exam starts off with a question that refers to a graph, which means that the answers from this question need to be given to two significant figures. And what was really remarkable about this, or this exam in general, is that there's lots of areas where significant figures actually played a role. I think it was 5 or 6 marks worth. So it's really important that when you're estimating, especially if it says estimate, make sure that you give your answer to two significant figures, because there's a very good chance that there's going to be a mark allocated to that. So question 13 is a photoelectric effect question. You've got different metal samples and you're shining different frequencies of light and measuring the maximum kinetic energy of the electrons emitted from the metal. So it's asking about potassium, and it's asking for the threshold frequency of potassium from the graph. So the threshold frequency represents the frequency at which you have just started to emit electrons. So they have the lowest, so essentially you want to find out where it reaches zero. So I'll just draw my line down here, and it sort of intersects just a little bit above halfway. So I'm going to go ahead and say that's around 0.375 times 10 to the 15. I'm remembering that this is two significant figures, so I'm going to make sure that I put in my answer as 0.38 times 10 to the 15 hertz. I'm going to keep going. Another estimate question. Estimate the work function for the potassium from the above graph. The work function is given, again we're using potassium, is given by the intercept with the y-axis here. So I can see that it's just about negative 1.5 on the graph. So I'm going to go ahead and give my answer as 1.5 electron volts. Again, to two significant figures. As I keep moving, it's now asking me to use my value from part B, which is this one up here, to estimate the maximum velocity of a liberated electron light frequency. So if we want to know the velocity, we need to know the kinetic energy. So the incident light, subtract the work function. So the incident light is going to be 6.63 times 10 to the negative 34. Let's try that again. Times 1.2 times 10 to the 15. And we're going to subtract that work function that we've estimated, but that's in electron volts, so let's convert that to joules. And I get 5.56, oops, 556 times 10 to the negative 19 joules. I'm keeping a bit more precision than I need to. Now to get that velocity, I just rearrange the kinetic energy equation, mass of an electron, and I get this number in my calculator. And again, it's saying estimate, and it's even saying give your answer to two significant figures here. So 1.1 times 10 to the 6 meters per second. Now the last question is just saying what happens if we use the same frequency but lower the power shot on the metal. So if we lower the power, what that means is we're going to have less photons every second. So the current is going to be reduced while it's firing away, and the maximum current is also going to be reduced. So I'd expect something like this to happen. Now this point A, this represents the reverse voltage that results in the electrons with the most kinetic energy not making it back. Now because we're using the same frequency, that means we're going to expect the same maximum kinetic energy, which means that we expect the same stopping voltage. So something like that. So the same point A, make sure here for point B it's below, and here for point C it's also below. Again, because less intensity, or less power, less intensity means less electrons. Less electrons means less current. And there we go. All right, so the question 14, what you've got is a sphere that's being suspended within this electric field. This electric field has a negative charge at the bottom, which means that this sphere will be experiencing an electric force facing upwards. And it's also going to have gravity. Now, gravity has to be larger than that, otherwise the sphere will end up being pushed up and it will actually start moving up if it's greater. Instead, what you've got is the forces are all balanced by an extra force of tension from the string. So because it's not moving at all, the forces are balanced. So that's sort of what a free body diagram might look like. I don't think it asks you for one. So the first question is saying calculate the strength of the electric field. Okay, that's a pretty easy one mark there. So the electric field is the potential divided by the distance between the plates. So that's 180 over 1.2, and I get 150, and that's volts per meters, but you can also have it per coulomb. So 150 volts per meters. So it's asking to calculate the tension in the string. So referring to my sort of diagram up here, what I'm going to do is draw a vector diagram to sort of illustrate what I'm doing here. And this is, I always prefer this way rather than just deriving calculations. I have a weight force, which is your mg, and that's being counteracted by two forces. You have an electric force, and you also have a tension force. So that would mean that in terms of just the magnitude, you would have the tension force being equal to weight subtract the electric force. In that case, sorry, it's just going to be mg take EQ. If I sub in my values, 0.2, 9.8, using my value from above, make sure you use the charge of the sphere, not the charge of an electron, which we might fall into the trap of doing. Your final answer should be 1.55 newtons. There we are. So down here we've got the next part of the question. Now it's swinging, so now we're going to factor in probably circular motion by the looks of things. Bottom of the swing, okay, good. So you get being given a velocity. Now it's asking for a free body diagram while it's going through the swing. So at the end of the day, it's going to be the same as that one that I drew above, except we're not going to have them balanced, right? So we're going to have a weight force acting down, and then we're going to have a tension force acting up. But it's okay to go a little bit higher when you put in those two forces, tension and the electric force. Because what we expect, if I was to draw a vector diagram, is the weight force coming down and tension coming up again, and then the electric force coming up, and that would result in a net force that looks like that. A centripetal force. So down here it's asking to derive an expression of the net force acting on the sphere in terms of the forces in my diagram. So essentially, if I have a look at, again, I should probably label my diagram, shouldn't I? So we've got weight here. I'll call this tension. I'll call this Fe. Doesn't matter in that case. So this net force here is going to be equal to these two subtract the weight. So what I'm going to do is going to go tension plus the electric force subtract the weight. And this is all done in terms of magnitude. So I don't really care about directionality because I've used the diagram here. But as long as you make your answer clear in the exam that you know the direction, I don't think they're really going to be fussed. And lastly, we're now going to calculate the tension in the string at the bottom of the swing. So now we can factor in that circular motion. So if we refer to the diagram, the equation that I derived before, I can get tension as being equal to the centripetal force, subtract the electric force, plus the weight force. Again, in terms of magnitude. So in this case, my net force is going to be the centripetal force, and they've given me the velocity, which is really nice. And they've given me the radius, so put all this information in, 2.8 squared on R, 0.8. So there's my net force, or the centripetal force. That's equal to 1.96 newtons. Now, the electric force is going to be EQ, 53, 0.408 newtons. Okay, another answer. And finally, the weight force, mg. It's kind of annoying that the weight force is the same as your centripetal force in terms of the number. It gets a bit confusing. So now I've got three values that I can use. I've got 1.96 for the net force, I've got the electric force of 0.48, and I've got the weight force of 1.96. So I just need to put them in this equation here at the top, and I end up getting 3.51 newtons. And there we are. Okay, so question 15 is a standard projectile motion question. You've got a gymnast and she lands below the starting point, which makes it asymmetrical, but other than that, it's a fairly easy one to do. So first you need to calculate the vertical and horizontal components of the launch velocity. So you start with 3.1 sine 55. To get the vertical one, you should have 2.54. And 3.1 cos 55, you should get 1.78. So what's remarkable about this question is part B gives you 5 marks just for figuring out how long she spends in the air. Now the answer kit that they've given has like a wide variety of ways that you can solve it, but by far the easiest way is just to solve the quadratic. So looking at the vertical motion, you have S equals ut plus half at squared. Sub in the values, so negative 1.25 because she lands below. Her initial velocity is upwards, and again gravity is acting downwards, so it's negative. Rearrange the equation so that it's equal to 0, and now you've got your quadratic. You can either use your formula or your calculator. You'll get 2 answers, and of those 2 answers, one of them is negative, so the only right answer must be 0.827 seconds, and all that for 5 marks. So calculating the range is a fairly easy one as well. You just want to use that horizontal motion now. S equals Vt, sub in the values. Now you know the time, so you get 1.47 meters. And the kinetic energy, you don't want to fall into the trap of thinking that at the top of the flight her velocity is 0. And that is true for the vertical motion, but for the horizontal motion, she's still moving at that 1.78 meters per second. So only a horizontal velocity, which means the kinetic energy is a half mv squared, and we're only going to be looking at the horizontal motion. So half 42.5. 1.78 squared, and that should be equal to 67.32, 67.3 joules. There we go. So question 16 is a graphing question, and it sort of touches on Snell's law, where you'll be graphing essentially the angle of incidence and the angle of refraction. So I'm going to go ahead and fill in all the values and plot the data points, and then I'll talk you through the analysis. It's important that in this graph we use 3 significant figures because the question explicitly says to use 3 significant figures. Okay, so now I'm going to graph my data points. So I'm going to zoom out a little bit. Now I'm going to draw my line of best fit. Okay, and there's my line of best fit. What I'm going to do first is go up the line, and what I see is that it crosses this part of the axis for me, which is really nice. And I'm going to start at the top end and then come down, and I see that it crosses the axis here. So that way I can use these 2 grid lines to identify 2 points for the rise and run. So what I'm going to do first is I'm going to draw a triangle just so I make it really clear to the examiner that these are the 2 points that I'm using. I'm just going to annotate these 2 points. It might not be necessary, to be honest with you, when you're writing your exam, but just to make things really clear. Oops. So now I'm just going to write my rise and run here on the graph. So the rise is going to be 0.85 subtract 0.55, so I get 0.30. The run is going to be 0.57 subtract 0.37, so I get 0.20. Which is really handy. So the slope of that graph, or the gradient, is rise over run, which is 0.3 over 0.2, which is equal to 1.5. Okay, now I'm going to start writing my answer on the next page 2 here. So it's not saying that the gradient is equal to the refractive index, so I need to show that I understand that the gradient in this case is equal to the refractive index. So what I'm going to do is just first restate understand what the gradient is from my graph. Rise over run. I probably should have given a bit more space on this question. And that's equal to 1.5. So the thing is, based on the equation that we have here, this equation, come down, and based on that, I can rearrange that and get N2 by itself, where the refractive index of air is 1, sine angle of incidence, over sine angle of refraction. So I know the sine of angle of incidence divided by the sine of the angle of refraction is actually the rise of a run in the graph, if you look at the units, or if you look at the axis titles. So that means it must be equal to 1.5. I don't need to do anything else. There's a few other ways that you can illustrate that you understand that too. Okay, so it's asking about 2 phenomena listed in the question. So looking up, so the first one would obviously be the refraction. So there it is there. There's my refraction. And then here it says that they, where is it? There we go. They found this rainbow effect. That rainbow effect is known as dispersion, which is also in the syllabus. There is no diffraction or anything here. It's the only ones listed were refraction and dispersion. Okay. So the next part of the question is asking about the percentage error if the tolerance for the angles or the error for the angles themselves was positive and negative 1. So it's asking these calculations in my answer, and it wants you to talk about how the percentage error for the angles changes, not the sign of the angles. So it's not as difficult as it looks. So what I'm going to do is I'm going to just show some calculations. So for 10 degrees, the percentage error is going to be 1 in 10, so it's going to be equal to 10% error. For 30 degrees, so I'm slowly increasing, it's going to be 1 on 30. I mean, you can show using proportionalities as well, but any sort of demonstration that you can show, and just to sort of really solidify it, 52% error. So therefore, as the angle increases, the percentage error decreases. Probably should do this. Okay. This is the part where it might look a little complicated here at the bottom, but it's not. It's giving you a trig identity. It's saying if the angle of incidence was 50 degrees, remember it's plus or minus 1, because the tolerances are all 1 degree. Use this trig identity to work out the percentage error for that particular angle. So you just do this. So the A is 50 and plus or minus 1, right? So now I'm just going to, wherever there's an A, I'm going to put in 50, and wherever there's a B, I'm going to put in a 1. Cos 1 plus or minus cos 50 sine 1. And if I resolve those values, I get 0.766 plus or minus 0.0112. So that means that the percentage error is going to be equal to, just the way you do it for any other absolute uncertainty, area divided by the number, or the measurement, times 100, and you should get 1.46%. There's a few other ways you could do it, and you'll get something on the order of that number, and it looks good. Okay. Okay, so question 17, you have a banked angle question. You've got a plane, it's under its own weight force, but it's generating lift, or in this case, they're calling it upthrust, which is a little bit annoying, and that's resulting in a horizontal circular motion. So the first thing is it's asking to draw a vector diagram showing how the weight force and upthrust produce a resultant centripetal force. So I'll draw first a down arrow to represent the weight force, and then the upthrust force would look like that. I'm going to call it R. Now, based on this diagram at the top, the angle theta is going to look like that, and the resultant force, your centripetal force, is going to be like so. And there we are. And part B is just using trig to find out what the centripetal force will be. So you know that tan theta is going to be equal to the centripetal force divided by the weight. Therefore, the centripetal force is going to be equal to the weight tan theta, which is mg tan theta. Sub in those values, 15 degrees, and you get 14705. So your answer will be 1.47 times 10 to the 4 newtons. Okay. Now with part C, now it's asking you, well, now that you know the centripetal force, it's giving you the speed and asking you to figure out what the radius of the circular path is. So the first thing you need to do is convert that 450 kilometers per hour into meters per second by dividing it by 3.6. You'll end up with 125 meters per second. Very nice number. So the centripetal force is mv squared on r. And we already know from above that that's equal to 14705. So now rearrange that, we get r is equal to mv squared on 14705. Sum in the values, you end up with 5,950. So 5.95 times 10 to the 3 meters. Okay. Question D is asking you to do a bit of explaining, and it gives you a bit of space above. So it's asking you to explain why you would need to increase the speed if you're going to maintain altitude while banking. So the first thing I'm going to do is draw some diagrams. So I've got a weight force coming down, and in normal flying straight sort of thing, the upthrust is just going to match that, and the plane will continue to move with the constant altitude. Now, if I decide to bank, the magnitude of the upthrust remains the same, but notice that it doesn't reach the same height as the weight anymore. So the vertical component is lost. So the resultant force is not perfectly horizontal. So what I need to do is speed up so that the upthrust is a larger vector, so that I end up with a result that looks like that, and that can be a centripetal force. Just label it and sort of show that, you know, this is what happens when you speed up, like so. Okay, so now I need to use some words to sort of explain what I'm talking about. So here we go. I'm going to say the upthrust acts perpendicular to the wings. And that's important because when you move the wings, you change the direction of the upthrust. So when banking, the upward component of the upthrust vector decreases. Thus, more upthrust is required to keep the vertical component of the upthrust equal to gravity. When I say weight. Upthrust, final point, is produced by increasing the speed. Therefore, increasing the speed is required to maintain altitude. And there we go. Okay, question 18. It's a pretty intense one in terms of both conceptually and in terms of the mathematics behind it. So let's just get stuck into it. You've got two particles that are they're colliding together. So they have a certain amount of mass/energy beforehand, and then when they combine, they're going to have a certain amount of mass/energy afterwards. So what we're going to do is we're going to find out what the mass of the combined particle is in terms of the mass of the original particles. So what that means is that if I get the energy of both of the particles, so 2 times their original relativistic energy. Now this is according to the observer in the middle. That has to be conserved, which means that has to be equal to the mass of one particle afterwards. I'm going to call them m prime, c squared on 1 v squared on c squared. Now both particles, according to the observer, are travelling at 0.6 c. So I'm going to sub in 0.6 squared, okay, and then at the end we have m prime c squared, and afterwards they must be traveling at 0 squared if you want to square it. Okay, so now we can see that the c squares here will cancel out, and I'm going to resolve this bit on the left hand side and get 2m on 0.8, and that's going to be equal to just m prime, and keep going with that, and that becomes 2.5 m, which is great, which means the mass of the combined particle is going to be 2.5 times the mass of the initial particles. Okay, part B is asking to explain why the velocity of the combined particle must be 0 meters a second. So this is how I'd go about it. I'd say each particle had the same magnitude of momentum initially, but in the opposite direction. So what that means is that the sum of their momentums before the collision was equal to 0. So with that in mind, and knowing that momentum must be conserved, so the momentum, or the velocity, of the combined particle must therefore be 0. Okay. So the next part of the question, we've got an observer now here sitting with particle B. So there's a bit involved in this question. It's saying to use the formless relativistic velocity addition. So it's sort of giving you the hint of what you need to do in order to show that, or to determine the momentum of the system before the collision. Okay, so we first know that the momentum of B according to X is going to be 0, right? Because B is not moving relative to X. So we can say the momentum of B is equal to 0. So now I need to find the velocity of particle A according to particle B, or according to X, it doesn't really matter. So I'm going to use the formula VA prime, or same as saying we know what is U prime, and then just sub in those values. Okay, and then here we go. Right, so then I just work this through and I end up getting 1.2 over 1.36, which is equal to 0.882c. So that is the velocity of A according to B, or according to X, and that's important. So that velocity is the only thing contributing to the sum of the momentum. So starting with that idea, the sum of the momentum is going to be equal to the momentum of just particle A. That's going to be equal to mv on square root of 1 take v squared on c squared. Sub in those values. So now instead of v, I have 0.882 of c. It looks a bit like that, and then I end up getting 1.872 mc. So it's already wants it in terms of mc, so it's just 1.87 mc. And there we go. So now with part D, what it wants me to do is to work out what the momentum of the system after the collision will be. So I'll start by just making sure that we understand that according to X, the velocity of the combined particle will be 0.6c. Because if we have a look at this diagram, so this particle up here is moving in. Now X is moving with the particle, but once they collide, they're both going to be here while X continues to move. So after the collision, the combined velocity, or the velocity of the combined particle is going to be 0.6c, or 0.6 to the right. So with that in mind, I would say the sum of the momentum is going to be 0.6 m. Now if the combined particle has that mass on it, the m prime mass, over square root of 1 take 0.6 squared. So now to sub those in, the 2.5 from the very first part, c square root of 1 take 0.6 squared. And what I end up getting is 1.5 over 0.8, which is equal to 1.87 mc. And then I need to state at the end, therefore, same momentum as part C. And there we go. Okay, so in question 19, what you've got is a compass, which is effectively detecting the Earth's magnetic field, and then what you do is you generate another magnetic field to add on top of that, using a current-carrying conductor. So the diagram isn't particularly helpful in the way that it has north sort of on the left-hand side, but what you've got is a needle here, and then this needle will turn because it's going to be, what you're going to do is you're going to create a magnetic field that sort of wraps around like that as the current goes through it. And after that happens, what you have is the compass is detecting both of those, both the Earth's magnetic field, or the horizontal component of that field, as well as the magnetic field generated by the conductor. Okay, so let's just get to it. Part A is asking to calculate the field strength of the wire's magnetic field. So that was probably the easiest of the questions. You just used the formula that's in the data booklet. You have your mu naught over 2 pi multiplied by the current over R. And you sub those in, 0.05. That's the distance between the conductor and the compass. And what you should get is 1.48 times 10 to the negative 5 Tesla. Or down here I should put it, 1.48 times 10 to the negative 5 Tesla. Okay, so the next part is where you start to look at the concept, or whether or not you know the concept. So it's saying to calculate the strength of the horizontal component of the Earth's magnetic field. So if we remember back to that diagram, we have the needle sort of sticking or deviating this much instead of what it was doing. It was sort of facing this way, which was north, which was, like I said, very unhelpful. Because it was facing that way, that meant that this one here is the magnetic field, or the horizontal component of the magnetic field due to the Earth. So I'm going to call it E with a little H next to it. I hope I don't forget to do that. And that's now combining with a magnetic field produced by the current carrying conductor. So we've got BM, the magnetic field. Yeah, I'll just call it that. That's all good. And then I can just use trig to solve for that. Now it says it deviates by 80 degrees. That's the angle there. So I'm going to use this angle here. Tan of 10 is equal to the BEH over BM. Now what I can do is just come through here, rearrange, get BM tan 10, and you end up with 5 times tan 10. And I get 2.617 times 10 to the negative 6. So 2.62 times 10 to the negative 6 Tesla. So remember, the Earth's magnetic field is only horizontal really at the equators. So even though the compass is measuring the horizontal component, the next part of the question is asking you to figure out, okay, well, you've worked out the horizontal component. What is the actual magnitude of the magnetic field as it comes out at 66 degrees? So in other words, the needle, so if this was the new compass, I suppose, if it's sort of doing this, right, what we've measured using a horizontal compass looks like that, and that's going to be our BEH. And what it's asking for is, what is BE? Now, it tells you in the question that the magnetic field is at an angle of 66 degrees. So I'll say 66 degrees. So now it's just a trig problem, and not a very hard one at all. So cos 66 is equal to BEH over BE. So again, just rearranging, using our answer from above, and I got 6.433 times 10 to the negative 6. So my final answer, 6.43 times 10 to the negative 6. And there we go, that's section 2 done. Okay, so section 3, comprehension section. The first article is on X-ray fluorescence spectrometry. So as we go through, there's a few questions. The first page is a lot of sort of explanation stuff, so I'm just going to push through them. So the first question is asking for 2 properties of X-rays that make them suitable for fluorescence spectrometry. High energy is pretty important because you're going to need these X-rays to interact with matter, aren't we? So that's the first one, and I would also argue that higher penetrating ability as well, because you want to go through those layers, which it's so important for. Okay, and part B is explain how we know that the original painting had lances of different lengths. The response to this just comes pretty much straight from the article, so I'm just going to go through and try to paraphrase what it was saying. X-ray spectrometry allows us to see different layers, so the key being the different layers of the painting. So the next point I'll make is the different layers reveal that Rembrandt made corrections to lower layers, such as the lances of different lengths. Okay, part C is give 2 advantages of using X-ray spectrometry. Again, this is in the article. The answer key that the WACE marking key pretty much has quotes from the article. Again, I'll try to paraphrase. The first one being that it's a harmless way. So it's a harmless method to investigate expensive paintings, because you're not actually pulling the layers off or anything like that. You're just you're firing X-rays beneath the layers, but beneath the top layer. Okay, number 2 is essentially the painting can be returned to museums while the data is being analysed. the quote they have, I think, is restored securely where the public can still be can still enjoy them. Something like that. Anything along those lines and would be acceptable. So the next one is explain why the fluorescent radiation is element specific. Again, you're looking at the article. You would start off by going, okay, well, each element has a different number of protons, or as the article refers to it, the Z number, which is the charge on the nucleus, right? So what I'm referring to specifically is this here. This is where you get the information just above it and below it. So, charge of the nucleus. Why does that matter? Well, then you keep going with your explanation. So, fluorescent radiation depends on the energy transitions, which are dependent on the number of protons. And then to really solidify it, I'm going to chuck in the equation that they give. That's not the right E. We're doing which is Z squared on N squared. Let me just double check. Yeah, that one. Okay, so moving on to the more mathsy stuff. So part E is about estimating M and L. To answer this, you still need to have a bit of knowledge from the article here. So it's asking you for the values of M and L relative to the K shell for iron. Okay, so up here, you've got the K shell, and then as you go out, you've got L and then M. Now, what it's asking for is what are those values relative to K for iron. So for M, I'm looking for a K beta, and for L, I'm looking for a K alpha. So now I'll go back up the top here. Okay, so I've got here's my iron, an iron there. I've got K alpha and I've got K beta. So if you remember, M is K beta. So this one here is my M, and this one here is my L. So now what I want to do is I want to work out what those values are. So for K beta, or the M, just grazes that notch there, and that notch represents 7. So I'm going to go ahead and say 7.1. And then this one here comes down. I wish I had a ruler. That's a terrible one. Let's try that again. Okay, so again, not quite there, so 6.4 for that one. So 7.1 times 10 to the 3, because it was kiloelectron volts, and 6.4 times 10 to the 3 electron volts as well. Okay, that's good. And K is 0 because it's relative to itself. Now part 2, it barely gives you any space to do it, unfortunately, but it's asking you what the wavelength of the photon is as it goes from N to L. So the first thing you want to do is work out what the energy difference is between M and L using your values above. So 7.1 times 10 to the 3, take 6.4 times 10 to the 3, and I end up with 0.7 times 10 to the 3. And that's in electron volts. So in joules, that's going to be 1.12 times 10 to the negative 16 joules. Okay, so now that I have that number, chuck it in. I don't know why they really made this so short in terms of space. Okay, all good. Rearrange that formula. You end up getting lambda is equal to HC on E, 6.63 times 10 to the negative 34, 3 times 10 to the 8, divided by 1.12 times 10 to the negative 16 equals 1.78 times 10 to the negative 9. Remember, it says estimate, so 1.8 times 10 to the negative 9. And to which part of the spectrum does it belong? If you have a look at your data sheet, it falls well within the X-ray, which is what we wanted it to do. Okay, part F. How would the graph change if the operators of the spectrometer increase the power of the X-ray beam while keeping the wavelength constant? Explain your answer. Now, look, at the end of the day, I didn't like this part of the question because if you look at it, importantly, it says that this is the relative abundance. So if you increase the power, you're going to increase the number of photons, but it won't change the relative abundance of each of those peaks. You might reduce noise, I don't know, but the problem is this scale is essentially it's normalized. So what you want to do, or what I would say here, is that there is no change. And when explaining that, I would illustrate my knowledge and say, well, look, more power means you're going to have more photons per second, so you can expect to have a higher abundance overall. However, the graph does not show how many photons or the intensity. shows the relative number of photons or intensity. So I'll say the relative abundance, which is what it does show, of the photon energies, be specific, the different photon energies, will not change. Okay. Okay, and the last question in the exam, number 21, is on drift velocity. I guess it's more about the Hall effect, I think. So the first part of it is actually just a straightforward calculation. So it's giving you the equation at the top here, VD on 1 on NAQ. So you just plug and chug, really. Over NAQ, just sub in those values. There we go. And you get 2.206 times 10 to the negative 4. So 2.21 times 10 to the negative 4 meters per second. And we hopefully already know that the drift velocity of, the drift velocity is typically fairly slow. So that's good. Okay, so question B is asking to explain why the Hall voltage, or VH, reduces to 0 when the conducting strip is moved in the correct direction and at the correct speed. So just really quickly, if we have a look at this diagram here, what you've got is a current that's passing through the strip like so. And as it does so, if there's a magnetic field, in this case it's pulling out, you'll notice that the force on the positive charge will be in this direction, and the magnetic force on the negative charge will be in that direction, which sets up an electric field between this side and this side. Now that electric field is what is measured by that, I suppose that's a voltmeter, that's the Hall voltage, I suppose. So the question's asking, if you move this strip at the correct speed and direction, how can you make it so that this equals 0? And the answer is about basically if you move the strip backwards at the drift velocity, then the movement of the electrons inside here, which will be moving this way, but the movement of those electrons will be counteracted by the velocity of the strip, which means there won't be any movement relative to this magnetic field. And if there's no movement relative to that magnetic field, then they won't separate out and create a potential difference. So that's sort of what you want to say in your answer. So this is how I do it. If the strip moves in the opposite direction to the electrons, their relative velocity to the magnetic field is 0. Okay, so we know that F equals QVB. So if that's the case and the velocity is 0, then the electrons will not experience any force. So the charges won't separate, and if the charges don't separate, then you have no electric field, and therefore no potential difference will be detected. All right. Part C is asking why increasing the magnitude of the magnetic field will increase the Hall voltage for a stationary strip when equilibrium is restored. I don't like that it says when equilibrium is restored. It's kind of a bit confusing. But basically, when the strip back to the way it usually is, it's not moving in the opposite direction. If you do increase the magnetic field, why will you experience an increase in the Hall voltage? And again, this is sort of, to be frank, this is just, it's the same. It's asking this for the same sort of knowledge. But let's just go through it. So what I would say, since the magnetic field is equal to the QVB and the Hall voltage depends on that force, which we've already sort of talked about above, then we can say that the Hall voltage is proportional to the magnetic field that it's under. So if you increase the magnetic field, you give a greater force, and that gives more charge separation, and therefore if you increase the charge separation, that's a stronger electric field and a larger potential difference. Okay, so there's that one. Okay, so part D is actually a fairly easy one. If you just look at your data booklet, you'll see this here. Electric force on Q, that's equal to V on D. Now, in this particular case, we can apply what we've got in the article to this formula. So the V in this formula is equal to the Hall voltage. And the D is going to be equal to the width, and the force is the electric force. So with that in mind, we can say that the electric force on Q is equal to the Hall voltage on W. And then rearrange that, and you end up getting what they need. There we go. Okay, and part E is to calculate the Hall voltage while it gives you all the information you need. So what I would do is I would start off with an equation that gives me the Hall voltage as a starting point, and that one is given to you in the article as Fe equals VHQ on W. And we also know that Fe is given as QVDB. And we also know that VD is equal to I on NAQ. So if we sub those in, if I sub this VD in on the right hand side here, what I end up with is VHQ on W is equal to IQB on NAQ squared. So I get VH by itself, Q squared. That Q will cancel with that squared. And that will leave me with I, which is 26, B, 3.5, W in meters is 0.03. And I want to get that over 8.5 times 10 to the 28. And the area is just the length times the width, so 0.03 over here, 0.001. Very easy to get that mixed up, I'm sure. 1.6 times 10 to the negative 19. And you end up with 6.69 times 10 to the negative 6 volts. Cool, and chuck my answer down here. 6.69 times 10 to the 6 volts. And of course you could do this in many other ways by resolving parts of it first. But there we go. And that is the end of the exam. So thank you very much.